Now let us talk about integrity rules. We have entity integrity and referential integrity. Entity integrity is the condition in which each row in the table has its own unique identity. Meaning, all of the values in the primary key must be unique, and no key attribute in the primary key can contain null. Since this is the first time that you are going to hear null, null is just the absence of any data value. It may be unknown attribute value, or it may be known in the context of the data, but they are missing in the database table, or you have an inapplicable condition. Like for example, the last name attribute is null for people in countries wherein you don't have a last name. Other integrity rule is referential integrity, in which every reference to an entity instance by another entity instance is valid. In other words, if you check the foreign key entry, it must either be null or there is a valid value that references a primary key of the related table. Let's take a look at an example. In this example, we have the table name product and the table name vendor. In the table name product, we have the primary key product code and foreign key vendor code. In the table vendor, we have the primary key vendor code and we don't have any foreign key. Now, to check the entity integrity, we take a look at the primary key. In this case, we take a look at the values of the product code and check for each of them if they are unique and if we don't have any null values. In this case, we can check that the product codes in the product table are all unique, meaning there are no repeating product codes and there are no null values. And so we say that the product table has entity integrity. You can also check that for the vendor table. The primary key is the vendor code, and as you can see from the table, the vendor codes are neither repeating and there are no nulls. So we also say that the vendor table has entity integrity. Now, for the referential integrity, we take a look at the foreign key. For the vendor table, we don't have any foreign key, and so we say that it is not applicable for the vendor table. Now, for the product table, we have a foreign key, which is the vendor code. The vendor code references the vendor code as the primary key in the vendor table. And so when we check each of the vendor code in the product table, it should be existing in the vendor table. So if we check 232, there is a 232 vendor code in the vendor table, 235, 231. So all of those vendor codes that are in our product table are all existing in the vendor code. In some cases, if there are null values in the vendor code, that is still also acceptable. So that's how we check if our tables have referential integrity and entity integrity. Now, the relational database integrity rules are very important to good database design. The relational database management systems enforce these integrity rules automatically. For the integrity rules, these are the requirement. So all primary key entries should be unique and no part of the primary key may be null. The purpose of this is so that each row will have a unique identity and foreign key values can properly reference primary key values. An example of which is this: no invoice can have a duplicate number, nor can it be null. In short, all invoices are uniquely identified by their invoice number. For the referential integrity, these are the requirements. Foreign key may have either a null entry as long as it is not a part of its table's primary key, or an entry that matches the primary key value in a table to which it is related. Meaning, every non-null foreign key value must have reference to an existing primary key value. The purpose of this is that because it is possible for an attribute not to have a corresponding value, but it will be impossible to have an invalid entry. The enforcement of the referential integrity rule makes it impossible to delete a row in one table whose primary key has mandatory matching foreign key values in another table. An example of which is a customer might not have assigned a sales representative number, but it will be impossible to have an invalid sales representative number. Now that we are all familiar with what null is, it is important for us to more or less minimize the number of nulls in our database tables. First, to address or handle the nulls is by creating flags. Flags are special codes used to indicate absence of some value. Or we can also implement constraints. Like for example, not null constraint, wherein you are placing this on a column to ensure that every row in the table has a value for that column. You can also have unique constraint, wherein you are placing a restriction on a column to ensure that no duplicate values exist for that column. Now let us talk about relational algebra. It is a theoretical way of manipulating table contents using relational operators. In this, we are going to talk about relational variables, or relval for short. Relvar is a variable that holds a relation. The heading of the relvar contains the names of the attributes, whereas the body contains the relation. The relational operators have the property of closure, closure being the use of relational algebra operators on existing relations produces new relations or tables. The first relational set operator is the select or restrict. It is a unary operator that yields a horizontal subset of a table. In this example, the original table has p code, p description, and price. If you're going to select all, it will yield the same table. But as you can see, it is a new table that is derived from the original table. Or if you're going to select with certain criteria like select only price that are less than $2, it will yield the table on the right, which has two results in the table. Or if you select only those items that has the P code 311452, it will yield the following result on the right. And as you can see, it yields horizontal subsets from the original table. The next relational set operator is a project, which is a unary operator that yields a vertical subset of a table. So from our original table earlier, p code, p description, price. If we're going to project through price, it will yield the table that only has the prices. If we project the p description and the price, it will yield the table containing only the two columns. And if we project using p code and price, it will give us as a result the table containing the p code and the price. Next relational set operators are union and intersect. For union, it combines all rows from the two tables, excluding duplicate rows. In getting the union of two tables, these must be union compatible. Union compatibility means that the tables share the same number of columns and their corresponding columns share compatible domains, and not necessarily in the same domain. For intersect, this yields only the rows that appear in both tables, and the tables must also be union compatible to yield valid results. In the example on the left, we are going to get the union and intersect of the two tables. For the first one, if we get the union, you can see that we are going to get everything, and we're just going to exclude the duplicates. In this case, the box fan already appears in the first table, but it also appears in the second table. So in the result, it will only appear once. For the intersect, we're going to check those data that are appearing in both tables. In the first table, we have student names. The second table, we have employee names. And as you can see, Franklin Johnson might be both students and an employee. But if we have something, if we're getting the union or intersect of tables that do not have the same domain, the domain in the first table will be followed. So in this case, in the result, you can see student first name and student last name. The next relational set operators are difference and product. The difference yields all rows in one table that are not found in the other table. The tables must be union compatible to yield valid results. Next is the product, which yields all possible pairs of rows from the two tables. For the example on the left, we can see we have one table on student's name and one table on the employee's name. If we're getting the difference, it means that we're going to check each of the names in the employee table and check if they are in the original table or in the first table. If they are, we're just going to eliminate them from the original table. In this case, We have seen earlier that Franklin Johnson appears in both tables, so our result would only include those names, everything that is in the student table, minus the name of Franklin Johnson. For the product, you can see that we're just getting all of the possible combinations. So for example, in this table, the first table, we're just going to get the combination of the three items that we have on the store table. Same goes with the lamp, box fan, etc., etc. So the total number of combinations that we may have is the number of data that you have in the first table multiplied by the number of data that you have in the second table. In this case, you have 6 by 3, so the resulting relation and table has 18 records.